Observing a piece of metal deforming under pressure, we witness a mystery of scale. How does a microscopic defect in a crystalline lattice know how to arrange itself to dictate the strength of the entire material? To understand this, we must analyze the mechanics, the external forces, and the complex interactions of dislocations. This equation calculates the elastic strain energy of a dislocation and represents the axiom that governs these behaviors. It depends on a geometric constant alpha, the shear modulus g, and the square of the Berger's vector magnitude. Because energy scales with the square of this vector, physical systems adopt configurations that yield the smallest possible b squared. Every complex dislocation behavior, from splitting apart to forming structural walls, is a physical attempt by the crystal to minimize this specific equation. This energy baseline leads to a practical consequence. A dislocation will alter its own geometry if doing so reduces its overall strain energy. We determine if a dislocation changes using Franck's rule. The diagram shows dislocation B1 splitting into B2 and B3. If the initial squared vector is greater than the sum of the resulting squared vectors, the reaction yields a lower energy state and occurs spontaneously. In a face-centered cubic lattice, the black unit vector 3 splits into two smaller green Shockley partials, 1 and 2. Squaring the initial vector gives 1/2 A0 squared, which is greater than the squared partial sum of 2/6. Therefore, this reaction is energetically favorable. This geometric split carries an engineering consequence. As the flowchart details, when a perfect dislocation dissociates to lower its strain energy, it leaves behind a region of mismatched atoms called a stacking fault. Stacking faults represent calculated geometric adjustments, allowing the crystal to shed elastic energy. Shift focus now from a dislocation at rest to one under stress. How do applied forces drive these defects to move? Movement requires mechanical work. This diagram shows a dislocation line segment moving a distance ds. As it activates, the segment sweeps across an area of the slip plane, performing work. We link this work to a driving force. By dividing the work performed by the distance moved, we isolate the glide force per unit length, represented at the bottom as FL equals tau times B. For three-dimensional stress states, we rely on the Peach-Kohler equation. This formula computes total force, using the applied stress tensor, the Berger's vector, and the line direction vector. Due to the cross product, the resulting force always acts perpendicular to the dislocation line. While external forces push a dislocation, the material resists internally through line tension. Because strain energy is proportional to length, the defect resists bending, acting like a stretched rubber band with a specific energy cost per unit length. Here, applied shear stress forces the dislocation to bow outward, while line tension fights to pull it straight. At equilibrium, these balance. Equating them derives the critical shear stress needed to maintain a bowed dislocation of radius r. Tau naught equals alpha GB over r. The macroscopic yield stress required to bend and move defects is dictated by the system's innate thermodynamic resistance to increasing its line length. What happens to the energy state when multiple dislocations occupy the same crystal space, and their individual stress fields collide? We establish a geometric framework to map this. Here, dislocation 1 sits at the origin, and dislocation 2 is located at position x, y. We apply the Peach-Kohler equation to determine how the stress field generated by the first dislocation physically acts upon the second. Substituting the specific stress components into the matrix isolates two distinct forces acting on dislocation 2, the force for glide, Fx, and the force for climb, Fy. This chart visualizes the mathematical output, showing the spatial distribution of glide force around the edge dislocation. It fluctuates between attractive and repulsive zones. Geometric orientation dictates this. Dislocations with parallel Berger's vectors generate repulsive force, while anti-parallel configurations generate attractive force. Contrast this with parallel screw dislocations. Because they lack normal stress components, the interaction matrix simplifies. As seen in the general equation at the bottom, they exert a purely radial force on each other. The push and pull between millions of microscopic defects is predictable through tensor mathematics, revealing hidden zones of geometric stability. When edge dislocations of the same sign approach, their respective compressive and tensile strain fields superimpose. This creates a severe energy penalty, pushing the strain energy to 4 times B squared. To prevent this, a physical repulsive force keeps them apart. Conversely, when opposite-sign dislocations approach, their fields cancel out. This drops the total elastic energy toward zero and drives the dislocations to annihilate each other. Because same-sign dislocations cannot annihilate, they migrate into geometric patterns to find the lowest combined energy state. This vertical stacking creates a stable alignment. By forming a wall-like structure, they minimize collective strain energy, forming macroscopic microstructures called low-angle grain boundaries. One final interaction demonstrates this drive: image forces. A free boundary acts as an energy sink for an approaching dislocation. Because a free surface offers no resistance to the displacement field, the force draws the dislocation out of the crystal entirely to relieve all strain. Dissociation, line tension, driving forces, and stable arrays are all direct manifestations of one physical law. The macroscopic strength, yielding, and failure of all crystalline materials are governed by the requirement to minimize fundamental elastic strain energy.